In this video, we will be looking at a few non-linear relations. So we're going to move away from the lines and see what other shapes scenarios can be represented by. So the promotions manager to a new band is deciding how much to charge for concert tickets. She has calculated that if tickets are $30 each, then 200 people will attend. So if we look at the following row, 30 ticket price, 200 people, the revenue or the money made would be the price times the number of people to get $6,000. Now she wants to maximize this amount that's coming in. So she has noticed that for every $1 increase in price, 10 less or 10 fewer people will come. So if we look at the next row, you will notice that for a ticket price of $31, 190 people will attend. So the revenue would be, or the money made would be the price times the number of people, which gives us actually less money, 5,890. Let's continue downwards to see if, at some point, maybe this does increase. So if we increase the price again, $32, the number of people will drop by 10 again. And if we do 32 times 180, we again get a lower number of 5,760. If we increase the price one more time, we will have 170 people. And if we do 33 times 170, we get 5,610. So this is just going downwards. So continuing to increase the price won't do anything. So let's work backwards. Let's decrease the price. Maybe if we decrease the price, enough people will come to make our revenue more. So for $29, an extra 10 people will come, so 210. So if I multiply the price by the number of people, I actually get 6,090. So that's more. So let's continue dropping the price. For $28, 220 people will come. And for that, 28 times 220 is 6,160. And if we keep decreasing the price, so for $27, we'll have 230 people. If we multiply that, you get 6,210. If you'd like, you can pause the video here to continue your chart and then come back to check. So as the price is decreasing, the number of people will continue to increase. And then for our revenue, we're just multiplying the price times the people. So 26 times 240 is 6,240. So again, we're increasing. 25 times 250 is 6,250, again increasing. 24 times 260 is 6,240, so now we're dropping a little bit. And 23 times 270 is 6,210. So looking at this appears to be the ideal situation. Sell the tickets for $25 to get 250 to come and maximize that revenue. Now let's go ahead and take this information and plot it in our chart. So looking at your page, you're going to look at number of tickets on the bottom and the revenue at the top. And you can pause the video here to fill in. You are going to have to estimate a little bit. So for $23, the revenue was 6,210. So roughly here. At 24, it was 6,240, so a little higher. Then 250, and then it drops back down to 240. Then at $27, we're at 6,210. Then we're at 6,160. 6,090. 6,000 exactly. 5,890. 5,760. And 5,610. So clearly this is not a line, okay? It's a curve, more of a curve. And if we connect the dots, we would end up with something like this. So you get kind of a curve shape. So if we were to describe this, you might describe it as a hill or an upside down U, whatever you may think. So looking here, I'll say both, hill, U-shaped, but the official name of that type of hill or U-shape is a parabola. And that's actually what we're going to be looking at in this entire unit. So describe the relationship between ticket price and revenue. So what we noticed is that as the ticket price increased, the revenue increased to reach a maximum and then decreased the rest of the way. Okay, so you saw that upwards and then downwards, which is very different from a line because a line would just go up all the way or down all the way at a constant rate. What is the maximum amount of money that can be earned? Well, we saw the maximum was right here. You could earn $6,250 and the ticket price was $25. Now, this point that we used is right over here. Okay, that is your maximum. It is called an optimal value. So an optimal value would actually include both a maximum and a minimum. But this special point is called the vertex. So it is the tip of the parabola. So the optimal value is called the vertex of the parabola. Okay, so we will see some new terminology related to this parabola. Let's try another example, and this time it's about a swimmer's dive. A swimmer dives into a pool and then submerges. The equation to model the height, y, in meters, the swimmer is above or below the water surface at x seconds is y equals 0.1x squared minus 1.2x plus 1.1. So y is the height, x is the time in seconds. We're going to complete the table of values to graph. Now I've already done a few of them. So at time 0, thinking back to table of values for lines, we would replace x with the value given. So I have x in two spaces, here and here. So I just replaced x with 0, and then you can plug it into your calculator or do BEDMAS. So at time 0, I got 1.1. At time 2, I replaced x with 2, and I got negative 0.9. And at time 4, I got negative 2.1. The negatives just mean that the swimmer is underwater. So let's go ahead and try the next one. So I'm going to write y equals 0.1, and then instead of x, I'm going to write 6, which is then squared, minus 1.2, and then again, instead of x, I'm going to write 6, and then plus 1.1. And now we can use a little bit of BEDMAS. So in BEDMAS, we do the exponents first. So that's the first thing I'm going to simplify. 0.1, 6 squared is 36, minus 1.2 times 6, and then plus 1.1. And the next operation in BEDMAS would be division, which we don't have, and then multiplication. So I'm going to do 0.1 times 36 is 3.6, and then 1.2 times 6 is 7.2, and then plus the 1.1. And if we do this, 3.6 minus 7.2 plus 1.1, we get negative 2.5. And then we can do it again for 8. So 0.1, and then instead of x squared, we're going to write 8 squared. And then instead of 1.2x, we'll write 1.2 times 8. And again, exponents first. So that's the only step I'm doing here. 8 squared is 64. The next step will always be the multiplication. 0.1 times 64 is 6.4. 1.2 times 8 is 9.6. And then your last step will always just be simplify this. So 6.4 minus 9.6 plus 1.1 is negative 2.1. the video and try number 10 and 12, and then come back to check your work. So for 10, you should have 0.1 times 10 squared minus 1.2 times 10 plus 1.1. This gives us 10 squared is 100. When you do your multiplication, 0.1 times 100 is 10. Negative 1.2 times 10 is 12. And then plus 1.1. And this should give us negative 0.9. And finally, for 12, your setup would be 0.1 times 12 squared minus 1.2 times 12 plus 1.5. And after you simplify, you do end up getting 1.1 again. So let's go ahead and graph this information. So at time 0, we're at 1.1. At 2 seconds, we're at negative 0.9. At 4 seconds, we're at negative 2.1. At 6 seconds, we're at negative 2.5. Then at 8, we're back at negative 2.1. At 10, we're back at negative 0.9. And at 12, technically you're at 1.1. Then we can connect these points. And again, you see this U shape, but this time it's going upwards. And now we have some follow-up questions about this. How high is the swimmer before he dives? So that would be the starting point, which is right here. And that height is 1.1 meters. That point should be familiar to us. It is the y-intercept, the point where your relation passes through the y-axis. What is the swimmer's minimum height? Well, that's going to take place right here. The minimum height is that negative 2.5 meters. The negative just implies that they are below water. Oh, that should go here. When does the minimum height occur? Well, the minimum height occurs after 6 seconds. And this is called the vertex, just like in the other scenario. So it's, in this case, it's the lowest point. Next, we're going to draw a dotted line through the vertex. So a dotted vertical line. Now you will notice when I draw this dotted line, it creates the symmetry. The left side and the right side of the parabola are identical. And you can even see that in the table of values, that the points are identical. The equation of this, it's a line, but it doesn't have a y-intercept. So it's not going to be y equals mx plus b. It does pass through 6 on the x-axis. So the equation is x equals 6. Which way does this parabola open, up or down? So the opening at the top is upwards. So that means it will be up. And just as a little reference, this means up, this means down. And finally, when does this swimmer hit the water surface? Well, they hit the water surface here at 1 second when they enter the water. But then they come out of the water, and at 11 seconds, they hit the water surface again. These are called the zeros or the x-intercepts. So it's when the height is 0. That's where the name comes from. So we're looking at when this parabola hits the x-axis. So now we have y-intercepts that are important and x-intercepts that are important. So that's just some terminology, and you'll see it more later on as well. Now let's just do a little comparison between linear and quadratic. And quadratic is what these parabolas are resulting from. So in terms of the graph and the shape, a line is just a line. A quadratic is the parabola. In terms of the equation, we know the equation of a line is y equals mx plus b. we know that for a quadratic, if you saw the previous example, there was an x squared in there. So the original equation is y equals ax squared plus bx plus c. It is this x squared term that is super important. Sometimes the x term is missing or the constant, but as long as that x squared is there, it will be quadratic. So the variable in a line is just an x. But in a quadratic, there's going to be an x squared term. Okay. So let's look at our last one. Given y equals 2x squared minus 4x, is this relation linear or quadratic? Well, first of all, because you see that x squared, that makes it quadratic. Because there is x squared. So let's fill in the table of values just like the swimmer equation. So instead of x squared, I'm going to put a -1. So y equals 2, and then -1 squared minus 4, and then -1. Notice the constant missing? That just means there's less work for us. So -1 squared is 1. And then we can do our multiplication. So 2 times 1 is 2. -4 times -1 is 4, and 2 plus 4 is 6. So the coordinate, -1, 6, for when we plot it. Let's try 0. Y equals 2 times 0 squared minus 4 times 0. We should know 0 times anything is 0. So technically, when I do 2 times 0 squared, it's going to be 0. 4 times 0 is 0. 0 minus 0 is 0. So your next coordinate is 0, 0. Next one, y equals 2, and then instead of x squared, I'm going to put 1 squared minus 4 times 1. Clean up, exponents first. So 1 squared is 1. Now multiplication. 2 times 1 is 2. 4 times 1 is 4. But this time we have 2 minus 4 to get -2. So here's our next coordinate. And why don't you pause the video to try the last two on your own, and then come back to check your answers before we plot them on the graph. So you're going to have 2 times 2 squared minus 4 times 2. 2 squared is 4. And now to clean up, 2 times 4 is 8. 4 times 2 is also 8. And that gives us 0. So 2, 0 is another coordinate. And we should already be seeing that symmetry in the fact that the y value is repeating. And finally, 2 times 3 squared minus 4 times 3. 3 squared is 9. Now for the multiplication, 2 times 9 is 18. 4 times 3 is 12. And 18 minus 12 is 6. So our last coordinate is 3, 6. And let's plot this. -1, 6 is up here. 0, 0 is the origin. 1, -2. 2, 0. And 3, 6. When we connect the dots, we will try to make a smooth curve. And then we will put arrows at the ends for good communication. And just going back to those terms that we saw in the swimmer example, here is the tip of the parabola. That is the vertex. Here is where your parabola passes through the y-axis. So that point is your y-intercept. The zeros are where you go through the x-axis. So that would also be 0 again, but also 2. And finally, your axis of symmetry would be the line that cuts the parabola in half. And we will see those properties more in another lesson. But there it is. These are quadratic relations. You notice them because of the x squared, and they create this parabolic shape.